So this part. So I have assumed that this Walsh theorem, and then I have proved it, the elementary renewal theorem. So here first we put the Walsh theorem. Okay. So statement of the Walsh theorem is clear that n is a stopping tide with respect to xi. Then expectation of summation y is equal to 1 to n xi. This is same as expectation of n, and then expectation of x1. Okay. Okay, how to prove it? Okay, so in particular, I need expectation of n that is finite. That is actually you can think of. That's not a big deal. So to prove these things, we are considering kind of a truncation thing. So I am defining a random variable zi, which is 1 if my n is greater than or equal to I. Okay, and then 0 if my n is less than I, means I am truncated there, zi. Okay, so now this zi, this is determined by however n is less than I or not, no? Because it is 0 and otherwise it is 1. That is, so if n is less than I, that means actually it is determined by my x1, x2 up to x of I minus 1 is strictly less than I, n is strictly less than I, and n is nothing but the stopping times. That means, so basically n is equal to, if you look at k, then that is independent of x of k plus 1, x of k plus 2, and so on. So this zi, this is determined by the random variable x1, x2, and x of I minus 1, and thus it is independent of xi. Okay, so now I will try to use this thing. So expectation of what I want to know, I want to show these things. So now these things actually I can write down that this is same as expectation of, I can put summation over I is equal to 1 to infinity xi and zi, because for n greater or equal to I, this is 1, and for n less than I, this is 0. So I have basically I is equal to 1 to infinity xi zi. Now these things, okay, what I can have, this is summation over I is equal to 1 to infinity expectation of xi zi. Okay, this is expectation of xi zi, and now xi and zi, they are independent. So I can have this is summation over I is equal to 1 to infinity expectation over xi, and then expectation over zi. So here I see that you have infinite sum and then expectations. I have basically interchanged these summations and expectations. Why this is so? You just think of this can be done because it is increasing and so on. So maybe you can use this what is called the dominant convergence theorem to show that this happens. Okay. So now what I can write down, this part I can have expectation of xi, they are independent, so I can write down, say suppose this is expectation of x1, and the summation over I is equal to 1 to infinity expectation over my zi, and expectation of zi, that actually I can write down, this is same as my probability of n is greater or equal to I, is it not? So this is same as expectation over x1 summation over I is equal to 1 to infinity probability of n is greater or equal to I. This is the expectation of zi. I have from there how I have defined that part, because whenever n greater or equal to I, that is 1, otherwise 0. So expectation of zi is nothing but probability of n greater or equal to I. Okay, so now this is what? So n is basically your n greater or equal to I have, and n is the stopping time, so it takes 0, 1, 2, 3, and so on. So this is nothing but the expectation of n. So this is same as expectation over x1 and expectation over n. Okay, this is the Walsh theorem, proof of the Walsh theorem. What it says that if I have a stopping time n with respect to my xi are the iid, then summation over I is equal to 1 to n xi take the expectations, then the usual rule holds, means expectation over n and expectation over x1. Okay, this is the Walsh theorem. So we have used that part because, as I said, that to prove this elementary renewal theorem, we consider that nt plus 1, this is a stopping time, and then we used that part to write down to prove that mt by t, this converges to 1 by mu as t goes to infinity. Is it not? Because mt is a real number, mt is nothing but the expectation of mt, mean value of my renewal process. So what it says that for large t, that the number of renewals, expected number of renewals per unit time is basically is approximated to 1 by mu, where mu is the expected value of my interval time ti or ton. Okay, so today we'll talk about so-called the central limit theorem for renewal process. So before going to that, let us recall what is the central limit theorem for the sequence. Okay, what it says that, say, if you have, say, sequence x1, x2, xn and so on, so x1, x2, x3 and so on, suppose they are IID with mean and variance finite, so mean expected, or I just put it mu of is equal to expectation of xi, and then variance sigma, which is variance over xi. Okay, so then what I know from the central limit theorem, so basically what it says that if you look at the partial sum, say I think you denote by xn bar or x bar, I think that is nothing but summation over I is equal to 1 to n of xi. Okay, so then the central limit theorem says that this x bar, okay, basically it's depending on xn bar you can think of. So this xn bar, it asymptotically, it converges asymptotically with normal mean n mu, and then the variance basically n of sigma square. So in particular, if you have this xn bar minus n mu by sigma root n, okay, this is normal distributed, standard normal distributed with mean 0, variance 1, standard normal distributions. Is it not? This is the central limit theorem. That means for large n, okay, if you look at the sum of this my s of n, cumulative sum, that is basically the distribution is nothing but the normal distributed with mean n mu and then variance n sigma square. Okay, so we try to find out the similar kind of thing, but here I have n, means for each t I have nt. Okay, and then we try to see it how the central limit theorem for the renewal process. So basically central limit theorem is nothing but the asymptotic behavior, no, asymptotic behavior of by partial sum in this case. Okay, so that means for t large enough or for n large enough, what happened to my partial sum Sn? So that is nothing but it is normally distributed with mean and mu and variance L sigma square. So in a similarly, actually here we want to know that what will be the distributions for that and so on. Okay. So I'll try to write down first the statement of the theorem. What it says that, so let nt be a renewal process with interval times say ti, okay, and say let mu, which is my expectation of ti, and variance sigma square, which is variance of my ti. All are exist and finite, okay. They are the finite. So then that limit t goes to infinity and t minus t by mu divided by sigma root over t by mu cube. This is less than or equal to y is same as my phi of y. What is my phi? Phi is the cumulative distributions of standard normal variable. That means my phi of y, which is nothing but 1 by root 2 pi minus infinity to y to the power minus x square by 2 of dx. This is the cumulative distributions of the distribution functions of standard normal distributions. Okay. So like
आपका स्क्रीन मेरे के
yes,
स्क्रीन विजुअल नहीं हो रहा है.
स्क्रीन प्रॉब्लम है.
स्क्रीन दिखाई दे रहा है लेकिन जो लिख रहे हैं आप वो नहीं दिख रहा है.
नहीं दिखाई दे रहा है. अच्छा,
Yes, sir.
For all or only for you?
No, sir, it's for me also.
But I have asked you. Okay, let me check it once again. Is it visible now?
Yes, sir.
Yes, sir.
Okay, then I don't know why it should be the visible. Anyway, so what I'm saying that as t goes to infinity, there's an asymptotic behavior. Okay, so nt minus t by mu divided by sigma root over t by mu cube less than or equal to y. This is given by the cumulative distribution functions of standard normal distribution. Okay, that means phi of y, which is 1 by root 2 pi minus infinity of y to the minus x square by 2 d of x. Okay, how to prove it? So for that I'll use the central limit theorem for the sequence, in particular for the sequence ti's. Okay, so if I, in this case Sn is nothing but I is equal to 1 to n of ti, it is given to you. So that means my, as n goes to infinity, this Sn is normally distributed with mean n mu, variance n sigma square. Is it not? In particular, this is the same as limit n goes to infinity probability of Sn minus n mu by sigma root n. Is it not? By sigma root n. This is less than or equal to any y is same as my phi of y. This is central limit theorem applied to my the sequence ti's, because it has variance finite, mean is also finite, both exist, and hence actually I can use central limit theorem to write down this part. Okay, so now I want basically n of t. So then what is the relation? Already we know that Sn to p and t. So for that I fixed y. Okay, and let t goes to infinity, n goes to infinity, such that limit t goes to infinity, n goes to infinity, t minus n mu by sigma root n. This is actually equal to my minus y. Okay, so t minus n mu by sigma root n, this is minus of y. So that is the t converges to my n mu minus sigma root n y as n goes to infinity and t goes to infinity. So now let's look at these things, because Sn is less than t, okay, then I can have my nt, this is greater than or equal to n. So I put Sn is strictly greater than t. So for that case, what I can write down, if I try to let t goes to infinity, limit n goes to infinity of probability of that part, this should be same as limit t goes to infinity, limit n goes to infinity, probability of, I can write down, because I know the central limit theorem for my Sn, so I put Sn minus n mu by sigma root n. Okay, so this is greater than t minus n mu by sigma root n. Is it not? This part actually I can write down, and then this is same as limit n goes to infinity, probability of Sn minus n mu by sigma root n, this is greater than minus of y. Is it not? Because I wrote down already that part, that t, I fixed y such that limit t goes to infinity, n goes to infinity, t minus n mu by sigma root n, this is actually minus y. Okay, so this is nothing but actually I can write down, this is 1 minus limit n goes to infinity, probability over Sn minus n mu by sigma root n, this is less than equal to minus of y. Is it not? Because probability of a complement is equal to 1 minus probability of a. So now if you look at these things, this is nothing but 1 minus phi of minus y. Is it not? So now what we know of your cumulative distribution function, from there this is same as my phi of y. Is it not? Because 1 minus phi of minus y, that should be phi of y, because the total thing, if you integrate from that phi of as infinity, that is actually 1. So from there actually you are having that part. Okay, you check it, because you look at the symmetricity and so on, from there you will get it that 1 minus phi of minus y is same as my phi of y. Okay, so already we have proved it that nt, this is strictly less than n if and only if my s of n is strictly greater than t. Is it not? Basically we proved that nt is strictly greater than n is Sn less than or equal to t. So that means if you look at that, the complement set, this is same, because we start with Sn is greater than t. So if I have this part, then I can have my phi of y, which is limit n goes to infinity, t goes to infinity, then the probability over Sn is greater than t. That is actually I have shown it here. So now this is same as limit n goes to infinity, t goes to infinity, probability over nt is less than n. Is it not? And this part actually I can write down limit t goes to infinity, n goes to infinity, probability of nt minus t by mu by sigma of root over t by mu cube. This is strictly less than n minus t by mu by sigma root over t by mu cube. Okay, so now I try to find out the limit of as t goes to infinity and goes to infinity, what happened to this case. So now see that as n goes to infinity and t goes to infinity, what I know that t, this converges to n mu minus sigma root n y. Okay, so from here what I can write down, that n minus t by mu by sigma root over t by mu cube, this is, you check yourself, this is converges to y times root over of n mu by t, which again converges to y times 1 plus y sigma root n by t. Okay, to the power the square is there, so you put the square. Now as t goes to infinity, so this part goes to 0 and so this is goes to y, means this part goes to 0, so you have y. That means what I'm saying, that as n goes to infinity and then t goes to infinity, this part, okay, it converges to y. Thus what I have, my phi of y, which is limit n goes to infinity, t goes to infinity, probability over nt minus t by mu by sigma root over of t by mu cube. This is less than or equal to n minus t by mu by sigma root over of t by mu cube. This is same as my limit t goes to infinity, probability over nt minus t by mu by sigma root over of t by mu cube less than or equal to y. This is actually I want to show, no, this part. The asymptotically, that means what it says, that the central limit theorem for renewal process, it says that for large t, because t goes to infinity, that means for large t, my nt, this is normally distributed with mean should be now t by mu. Is it not? Mean is my t by mu, and then the variance is sigma square t by mu cube. Is it not? So for large t, that nt, what is the distributions of my nt, what it says that the distributions of nt is normally distributed with mean t by mu and variance sigma square t by mu cube. Okay, so limit t goes to infinity means in practice whenever it is large enough. Okay, so then we are saying that nt is normally distributed with mean t by mu and variance sigma square t by mu cube. Okay, let us consider one example where we can use central limit theorem. So when you can use the central limit, that means whenever we are looking for the asymptotic, means the asymptotic behavior and then the distributions of that. Is it not? Means for large t we want to know that how the distributions of that process looks like. So in that case you need to consider or you need to use the central limit theorem, like in your sequence case, no, that is for large n, and you want to know what will be the distributions of Sn, not this Sn, means I am saying that xn bar I wrote down. Okay, but here Sn is not Sn, in this case that is for the Ti sequence, which is interval times. Okay, let us consider one example and then see how we can apply. So now I want to know, so nt, this is a renewal process with TIs or IID such that my mu, which is expectation of Ti, this is set 10, okay, and the variance sigma square, which is variance of Ti, is equal to 4. It is given to you. So that means that NT be a renewal process with interval times Ti such that expectation of Ti is equal to 10 and variance of Ti is equal to 4. So what I want to know, so what is the probability that my n of say 1000, okay, lies between 96 and 104. That is actually I want to know. That means what is the, that means I want to find the probability of 96, okay, less than equal to n, okay, n 1000 less than equal to this one. Actually I want to know nt 1000. So you know, n 1000 means basically it is large enough. In that sense actually you are looking for n 1000. This is the in time, maybe if it is in something, it's not maybe hours or something like that. So n is 1000 I am considering, maybe more than that, that means it is large enough. So in that case, you need to apply the central limit theorem. That is the general thing, no? It may come to your mind that okay, I have to use the central limit theorem. Okay, so if you try to apply that part, you need to write down in your theorem setup, is it not? Because n minus nt minus t by mu divided by sigma sigma into root over of mu by, so t by mu cube. That form actually you have to write down. So I can write down these things is same as my probability over 96 minus 1000 by 10 divided by root over of 4 into 1000 by, is it not? Okay, there I have sigma times root over of mu by things, actually I will put it. So here actually I write down in this form. This part is less than z, which is less than 104 minus 1000 by 10 divided by root over of 4 minus, because if you just denote this part as my z, okay, because this is normally distributed, z is basically normally distributed with mean 0, standard normal distribution. So I put it 4 into 1000 by 100 cube, and then if you calculate these things, this is nothing but that probability over minus 2 less than z is less than 2. Okay, and from the table you can find out, because standard normal table is available to you. So from there actually you will see that this is nothing but 0.95. Okay, so what is the probability that n 1000 lies between 96 to 104 is 0.095. Okay, so similarly you can consider many examples in a practical sense and so on. You can make it. Okay, so you'll see in some assignment problem that I will give some assignment problem where you can use the central limit theorem for renewal process. Okay. Okay. So next we will do some applications, and for that I need some important renewal theorem. Okay. So mostly will not prove this theorem because that required more on that, but we'll use that renewal theorem and then try to find out. There is a concept called excess life and the total life of the renewal process and so on, and then we try to find out the limiting behavior of that life. Okay, the distributions of the limiting behavior and so on. So for that, first I try to state the important renewal theorem. So before that, I will recall some definition. It is called lattice. What is lattice? So a non-negative random variable, say x greater than or equal to 0, is said to be lattice if there exists a d positive such that if you look at x is equal to, since it is non-negative random variable, look at x is equal to nd and then take the probability, and then you consider summation over n is equal to 0 to infinity, that gives you 1. Okay, that means what it says that x is lattice if it takes only the integral multiples of some non-negative number. Is it not? So probability of x is equal to nd, then look at the probability. So then if you look at sum, that gives you 1. That means in the other point, okay, it does not take any values for that. So only it is taking the integer value or the integral multiple, not the integer value, because d may be some fraction number and so on. So it is the integral multiple of some non-negative number d. Okay, so x, a non-negative random variable, is said to be lattice if it takes only an integral multiples of some non-negative number d. Okay, there exists some d and so on, such that this happen. So in particular, if you look at the Poisson process, okay, so then what I know that it is basically Poisson process case with say intensity lambda is positive. In that case, what will be d? So for the Poisson random variable, in this case d is equal to 1. No, because it takes only the non-negative integer value. So basically 0, 1, 2, 3, 4 and so on. Is it no? So for Poisson random variable, it is d is equal to 1. Okay. And then we say that the period of a lattice X, what is that? Because there exists a D, no? So the largest D, this is the largest D having the above property. Is it no? The largest D having the above property. Okay, so sometimes actually we say that the distribution is lattice. That means if you look at random variable x and look at the corresponding distribution of x, if x is my lattice, then we say that the distributions f of x is lattice. This is just the definitions. Distributions of f of a random variable is lattice, means that the non-negative random variable is lattice. Okay. Now I will state two important theorem. One is called the Blackwell's theorem, another is called the Smith's theorem. Okay, that is two important theorem in a renewal process. I will state it, and then as I told you, I will apply this theorem to find out the distributions of certain things, asymptotic distributions basically. So what it says that so let NT, this is a renewal process. Okay, with renewal function which is empty. Then what it says that if f is not a lattice, then so not a lattice means whenever it is not lattice. Okay, so then what it says that limit t goes to infinity, look at the difference mt minus m of t minus a, this is equal to a by mu for a positive fixed. For any a positive, okay, for any a positive, what I can have that limit t goes to infinity mt minus m of t minus a, this is equal to a by mu if f is not lattice. So then question is, what happen if f is lattice? So that is given by part 2. If f is lattice, say with period d, then limit t goes to infinity, probability of Rn, which is equal to d by mu. Okay, so I put as a Rn, but here I consider t is equal to infinity. So what is my Rn? Rn is a random variable denoting the number of renewals up to nd. Okay, so then I put n goes to infinity, is it not? Because this is the number of renewal Rn up to nd. See, if it is up to time t, then we put nt, no? So here that's why r. Okay, you can put n of nd, that is also you can put it, that capital N of nd. This is, so whenever n goes to infinity, this is given by d by mu. So thing is that if my f, it has a lattice with period d, that means the taking values of my f, or in this case my ti's, because f is the distributions of ti's, they have the common distributions, no? So that means ti's, they are integral multiple of d, they takes values of integral multiple of d and d. Okay, so another theorem, as I told you, that is called the Smith theorem. So it's depending on whenever f is lattice or not, you see the things are different. Okay, the limiting behavior are different now. So Smith's theorem, or sometimes it is called the key renewal theorem. So since it is a key renewal theorem, no, it is expected that, okay, I will state it the Smith theorem, but this previous theorem can be obtained from your Smith theorem. Okay, in a particular case, that means this previous theorem or the Becquerel's theorem is a special case of Smith's theorem. That is why I try to put as a key renewal theorem. I will show it. Okay, let us first give the statement of this theorem. What it says, that let f be a distribution function of a positive random variable with mean mu. Okay, and I define a function h from 0 infinity to 0 infinity such that it has two property. One, h is non-increasing, and second, that it is integrable 0 to t h t 0 to infinity h t dt. This is finite. So it is non-increasing, that means it is basically decreasing, and it is integrable. H is my function. Then first condition is that if f is not a lattice, then what happens? Then limit t goes to infinity, zt so I define zt, which is equal to my ht plus 0 to t z of t minus x dfx. Okay, so this is the solution of the renewal equation. This is the renewal equation type, no? Because if you replace by h by f, okay, and z by m, that is the renewal equation, we have seen it. So this is a zt is a solution to this renewal equation. This is a generalized, means in a general form for particular z, that is gives you the renewal equation. Okay, So Z is equal to Ht. What is the property of H? That it is non-decreasing, and 0 to infinity H of t dt, that is finite. Okay, and F is the distributions of a positive random variable with mean mu. Okay, so if F is not a lattice, then what I have, that what can you say about the limit t goes to infinity z, the asymptotic behavior of that things. So this is nothing but 1 by mu 0 to infinity h of x dx if my mu is finite, and that I can think of 0 if my mu is equal to infinity. You know, because if mu is infinity, so this part is finite, so this gives you 0. Okay, so this is the case when f is not a lattice. And then what happens if f is a lattice? So if f is a lattice with period d, then for any 0 less equal to c strictly less than d, what I can have, that limit n goes to infinity z of c plus and d. This is nothing but 1 by mu summation over n is equal to 0 to infinity h of c plus and d if mu is finite, and 0 for mu is infinite. Okay, because since it has a lattice, f is a lattice, you look at z, actually it takes only the that integer multiple of the non-negative real number d. So I can have 0 is equal to c plus and d. Z z may not be talked because that is only for my x, okay, for the lattice, but z I have defined using this renewal equation. Okay, so it can take any value, but what it says that for any c where c lies between 0 to d, and then if you look at as n goes to infinity, look at what will be the z of c plus and d, then it is given by this form depending on the mu. If mu is finite, this is same as 1 by mu summation over n equal to 0 to infinity h of c plus and d, and 0 if mu is equal to infinity. It is similar kind of, no, this part 0 to infinity h of x dx I wrote down, but here it's little bit different, but because you have integration, so now I have summation here. Okay, because of this part. Okay, so I try to say that Smith's theorem, from the Smith's theorem one can deduce the Blackwell's theorem, at least for non-lattice case. Okay, let us try to see for the non-lattice case. Blackwell theorem is the special case of Smith's theorem. So for that one needs to use a special lemma. Again I am stating this lemma without proof, but one can use the Laplace transform to prove this lemma. So what it says that, now suppose a is a bounded function, then there exists one and only one function a, which is again bounded on finite intervals, that satisfies the following: at, which is equal to at plus 0 to t a of t minus y d of fy. That means if you look at, I wrote down that renewal equations in my Smith's theorem case, no, that zt is equal to h of t plus 0 to t z of t minus y d of fy. Okay, so what it says that this function is nothing but at, which is equal to at plus 0 to t So first I say that okay, there exists one and only one A on finite, means A which is bounded on finite number, which satisfy these things. Okay, and how the A looks like, I am saying here that A is looks like AT is equal to AT small at plus 0 to t small a of t minus y d of my. What is my m here? Again, the similar kind of thing, that mt, which is the renewal function. That means I can have that mt is summation over k is equal to 1 to infinity fkt. Okay, this is the renewal function. So I'll use this lemma, okay, in Smith's theorem, and then try to show that the Blackwell's theorem, in particular for non-lattice case, it is a special case of Smith's theorem. So to see this, I consider, so let a is positive, small a is positive, okay, it is given to you. Now I am defining the function hy, which is 1 if 0 less than y less than a, and 0 otherwise. Okay, so now if you look at the Smith's theorem, so what it says, that h should be non-decreasing, okay, it is non-decreasing, sorry, non-increasing, so it is basically, you can see that 0 to 0 less than a, y less than a, and I have, and also it is integrable, it is non-increasing, integrable positive function. So if you use this part and then apply the lemma what I told you, so then what I have, for all t is greater than a, my zt, which is should be my ht, because zt is what, zt is equal to ht plus 0 to t z of t minus x dfx, and the solution to these things is given by my lemma, is it not? So what it says, that it should be your ht plus 0 to t h of t minus y d of my, is it not? So if you try to write down that part, what I have, that the zt, which is solution to your renewal equation, is given by ht plus 0 to t h of t minus x dmx, is it not? So these things, and then if you try to write down what it is, nothing but, because of t is greater than a, this should be your t minus a to t d of mx, and this is nothing but your m of t minus m of t minus a, is it not? So, and another thing is that you check it, that a by mu, this should be 1 by mu 0 to infinity h of x d of x. So now for your non-lattice case, from the Smith's theorem I have that limit t goes to infinity of zt, this is, if my mu is finite, this is 1 by mu 0 to infinity h of x d of x, it is given to you. So that means nothing but this is a by mu. So I have that limit t goes to infinity mt minus m of t minus a, this is actually a by mu. Okay, for mu is positive, p is finite. So that means my Smith's theorem, the Blackwell's theorem is a special case of Smith's theorem. So for that I need to use this technical lemma, which one can prove it using the Laplace transformation. So but here actually I am not going to prove that part. Assume this lemma is true, and then you can apply here to get the Blackwell's theorem is a special case of Smith's theorem, at least for non-lattice case. Okay, these are the two main means theorem, and then you will use this theorem to find out the distributions of the different light. So for that, let us define. This is the definitions I am trying to make. What is the excess light or the edge? For T positive, we define delta T, which is nothing but T minus S of NT. Okay, this is called the edge. The edge. And then I want to look at called the residual line. Or the excess light. So this is nothing but the basically the interval of time. Suppose at time t the renewal has happened, and then for the next renewal you are waiting for that, and what is the time interval. So that means in the language, I mean in the notations, I put as a gamma t, which is s of nt plus 1 minus t. Okay, because at t you have the renewal has happened at time t, and then nt, so nt plus 1 the next renewal, and then this is basically nothing but the time interval, the waiting time interval. This is s of nt plus 1 minus t, and then we say that the total lifetime this is basically the I denote as a beta t, which is my gamma t plus delta t. Okay, so using this renewals theorem, we try to look at the limiting distributions of delta t, gamma t, and hence the beta t. And then we try to look at some examples in particular for the Poisson process case, because already we know that Poisson process is a renewal process, and we try to know what will be the lifetime, total lifetime for the Poisson process case, the residual lifetime or the excess lifetime for the Poisson process case, and so on. Okay. Okay, so let us first consider the residual lifetime. So as a theorem I try to write down what it says that, so let gamma t be the residual life or the excess life at time t, then what is the probability distribution, that probability of nu t is less than equal to x. This is the probability distribution. This is given by f of t plus x minus 0 to t 1 minus f of t plus x minus y whole of dmy. In addition, if f is non-lattice, then I can find out the limiting distribution. That means limit t goes to infinity, probability over nu t is less than equal to x. This is the limiting distribution, which is given by 1 by mu 0 to x 1 minus f of y d of y. Okay, so what it says that if the distributions f is non-lattice, then the limiting distributions of excess life is given by this formula, which is 1 by mu 0 to x 1 minus f of y d of y. Okay, so we try to prove these things, and then I will stop today. Let us look at the proof. So most of the cases actually, whenever we try to prove all these things, already you have seen that how we have proved these renewal equations. Okay, the integral equation for the renewal equation, integral form. So we try to take the conditional on the first renewal t1 is equal to x, and then we try to see whenever x is greater than t, or x is less than equal to t, and so on. Okay, so here also we try to use that similar kind of concept, and then the condition, and then the concept of total probability, and so on. Okay, let's see. So what is my nu t by definition? This is s of nt plus 1 minus t, is it not? So this is my nu t. That means you look at, so nu t is strictly greater than x for any x. So nu t is strictly greater than x means what? It means this is the if and only condition that if you look at interval t and t plus x, there is no renewal, is it not? Because nu t, this is strictly greater than x. So s of nt plus 1, this is greater than t plus x. That means, because at t we know that there is a renewal nt. So that means in t to t plus x there is no renewal. That means no renewal okay in the interval t to t plus x. Nu t is greater than x, that means s of nt plus 1 minus t is greater than x. So s of nt plus 1 is greater than t plus x, is it not? So that means what? That there is no renewal, because at t we know that there is a renewal, which is the nt. Number of renewal is at time t is the nt, and hence in t to t plus x there is no renewal. So okay, I take zt, which is my probability over nu t is strictly greater than x. Okay, these things actually I am considering zt. So I can write down my zt. This is 0 to infinity. Probability over nu t is greater than x, given t1 is equal to y, and then d of y, is it not? Conditionally on the first renewal t1, then which is probability of nu t is greater than x, I can write down that nu t greater than x given t1 is equal to y times d of y. So now I put as a y lies between 0 to infinity, and x is fixed to u, t is basically also fixed in this case. So then there are three cases. So case 1, what happens that if my y is greater than t plus x, y is greater than t plus x means basically what it says that, see, nu t is greater than x, nu t is greater than x, that means there is no renewal between t to t plus x, there is no renewal between t to t plus x. So if y is greater than t plus x, that means actually I can say, and t1 is equal to y, this is the first renewal at y, that means there is no renewal between t to t plus x again. Then there is no renewal occur at in t to t plus x, is it not? So probability of nu t greater than x given t1 is equal to y, this is same as that probability of no renewals in t to t plus x, is it not? So nu t is greater than x, I know that there is no renewals between t to t plus x. That means that these things, is it not? So I have made dfy, I think. Yes, dfy you have. So what I have, that this probability actually is equal to then 1. because probability of nu t greater than x given t1 is equal to y same as probability of there is no renewals in t2 t plus x, and already we have, because my nu t is greater than x, that means that there is no renewals in t2 t plus x. So this is actually 1, and hence what I have, that probability of nu t greater than x given t1 is equal to y, in this case probability of nu t greater than x given t1 is equal to y, this is basically 1, because this is same as that probability of no renewals in t2 t plus x. This is exactly 1, is it not? Because this is the sure event, we know. Okay, so case 2, if my t is less than y less than t plus x, so then what it is mean, that the first renewal at y, okay, so the first renewal happened at y, that is why t1 is equal to y, that means, and so in the interval t to t plus x there is only one renewal happen, because that is in y, is it not? So probability of nu t is greater than x given t1 is equal to y, this is actually 0, because here actually one renewal happened. So there actually we show that, okay, that nu t is greater than x if and only if there is no renewal happens in t2 t plus x, but for this case actually it is only one renewal happens, no, because that is at the point y. So the probability of these things actually is equal to 0. Okay, so then third case, that if 0 less than equal to y is less than equal to t, or this part you can think of, that is not a problem, because t1 cannot be 0, so there should be some renewal. So 0 less than y less than equal to y, less than, or 0 less than y less equal to t. So in this case what happened, that the first renewal happened at y, and then I can think of that process starts itself from y, okay, and the remaining is nu of t minus y, because first renewal happened at y, so I can think of that it start at point y, and then the remaining time, so that is basically the excess time should be t minus y. So probability of nu t is greater than x given t1 is equal to y, this is same as probability of nu of t minus y, which is greater than x, okay, and this is nothing but my z of t minus y. So now if you combine these three cases into here, I wrote down that zt in this integral form, which is using the total probability law, then what I can write down, that my zt, this should be 0 to t probability over nu t greater than x given t1 is equal to y dfy, and plus t to t plus x, there is means that probability is actually is equal to 0, no, and then from, if y is greater than t plus x, that means t plus x to infinity, then this is happening, no, probability of nu t greater than x given t1 is equal to y of dfy. Now you see, this is here actually it is exactly 1, and then this is 0 to t. This part I know that, because here my y lies between 0 to t, 0 less than y less equal to t, and hence I can think of this is the process start at y, and hence the excess time should be in between the remaining the remaining time means t minus y. So this is my z of t minus y dfy, and plus this is 1, so this is d of fy, and we know that f is a distribution function, so at infinity which gives you 1, so this is nothing but the 1 minus f of t plus x. So what I have zt, which is 1 minus f of t plus x plus 0 to t z of t minus y of d of fy. So now you see that it is of the form of lemma. So only thing is that I have to show that this is bounded, but this one is bounded because f is your distribution function. So 1 minus f of t plus x is bounded. Hence, the one and only one solution to this renewal equation is given by this form. So zt, which is because you just write down as a no, this one in my previous lemma, technical lemma. So this is 1 minus f of t plus x plus 0 to t. What was that? That is a of t minus y. Is it not? So you can write down this is 1 minus 1 minus f of t plus x minus y, no, 1 minus a of t minus y. So this is t minus y, now t is t plus x of my d of my. Okay, so zt, I have my this part, whatever I wrote down as a theorem form. Yeah, exactly this one. Why this is exactly this one? Because here zt, but I want basically, so zt means nothing but probability of nu t is strictly greater than x, is it not? So probability over nu t is less than equal to x, which is nothing but 1 minus probability over nu t is strictly greater than x. And then if you just look at from here, this is nothing but 1 minus z of t. Probability of nu t less equal to s is 1 minus zt, and zt is this thing, so 1 minus zt should be f of tx minus of these things. Okay, so this gives the proof of first part. Okay, so there we have not considered anything about my the distribution function, means whether it is a lattice or it's not a lattice. So now we will consider that if it is a lattice, non-lattice, then what happens? Because we want to show that limit t goes to infinity, the probability of nu t less than equal to x, the limiting distributions of x's life. Okay. So if f is non-lattice, so now the case is f is non-lattice. Then what happens? Okay, so mu is equal to expectation of t1. This is finite, no? So thus mu and f is a distribution function. So now you check, I can write down this expectation of x in a little different way, which is 0 to infinity 1 minus fx dx. Okay, you check by yourself, it is nothing else. And not only that, since it is there, I can write down that 0 to infinity 1 minus f of t plus x dt for its fixed x. These things actually I can think of if you just change the variable. This is x to infinity 1 minus f of y d of y. So now this one is finite because this is less than or equal to mu, which is finite. Is it not? So why I am considering this part? Because if you look at, if I try to use the Smith theorem, so there what I have this ht, which is non increasing. So now 1 minus fx is non increasing.
हाँ और क्या, सोचा तो था कि अब सब हो गया है, वैक्सीन भी सबकी हो गई है तो कुछ कर सकते हैं, पर सब कचड़ा हो जाता है।
What happened? Irna, what happened? Please mute yourself.
हम भी चलते हैं।
Irna, please mute yourself.
सही, ऊपर से ठंडी और पानी और हवा, पता नहीं क्या क्या चल रहा है।
Prerna, please mute yourself. So there, what I need that age, it should be non-increasing and it is positive. So it is positive, non-increasing, and it should be integrable, no? Because you wrote down 0 to t, h of 0 to infinity, h of t dt, that should be finite. That is integrable. So this functions is integrable and so on. Hence, by Smith's theorem or the key renewal theorem, what I can write down, that limit t goes to infinity of my zt, because zt it satisfies the renewal type of, yeah, this one, no, renewal equations. This is actually, you can think of my h of t. So if you look at the Smith's theorem for then z is equal to ht plus 0 to t z of t minus t and d of fy. So in that case I can write down, for non-lattice case, this is 1 by mu 0 to infinity h of, so 1 minus f of t plus x and then dx, which is same as 1 by mu x to infinity 1 minus f of y d of y. Okay, so therefore if I consider limit t goes to infinity, probability over nu t is less equal to x, which is 1 minus limit t goes to infinity of zt, is it not? So this is nothing but 1 minus 1 by mu x to infinity 1 minus f of y of dy. So now these things, this 1, what I can write down, this is nothing but, because mu already I have shown that 0 to infinity 1 minus fy dy, so I can put 1 by mu into 0 to infinity 1 minus f of y dy minus 1 by mu x to infinity 1 minus f of y of dy, and then you see this is nothing but 1 by mu, this is 0 to x 1 minus f of y of dy. Okay, so this completes the proof of the limiting distribution of excess life or the residual life for a renewal process. Okay, so this is the case when mu is already finite, because mu is nothing but the expectation of ti, that is finite, is given to you, and hence the limiting distribution of excess life or the residual life of a renewal process is given by 1 by mu 0 to integral over 0 to x 1 minus f over dy, where f is the distribution functions of interval times, common distribution function of interval times dy. So here actually on the thing is that f should be non-lattice. Okay, f is non-lattice. Yeah, so I stop now.